So there are some challenges associated with ISL. Some of those challenges are that it's highly complex because it requires bimanual activity with both our hands as well as a lot of facial features. Another challenge was the resources scarcity because it's a pretty new sign language and there are not much data set available across this. Another issue was the computational overhead. There was not that much GPU clusters available for the computation for me. And the fourth one is the temporal sequence has to be preserved because video is just a temporal sequence of frames. So that sequence has to be preserved. So now what our proposed strategy is all about. Let's say I do an action for you. I do not perform the entire video. It's like I just showed you four frames and it's like, okay, you can understand, okay, I'm talking about drinking tea. I could have done this, it's a video, it would have been like 30, 40, 50 frames, but I just showed you 4 frames and you are able to classify, okay, it's drinking tea. So why do not the model can do this? So that was the whole idea of our research, that how can we extract only the important frames and then pass it to the model to get the best accuracy and the correct classification. So what we did is, it's a 3-step process. The first step is subsample smartly. It means extracting the important frames out of it. Second is model space. It means understanding the spatial geometry of each and every frame. And the third one is the model time. That the third part will be actually joining the spatial information with the temporal information. So that's how our whole architecture looks like. In the starting one, we will pass the raw frames into a motion guided ROI extraction, which basically means when the video was recorded using Kinect, there was a lot of white background beside me. So we do not want that background. It was just like increasing my number of pixels and hence increasing my computation. So what I did, I just do the pixel mine, like apply the Gaussian filter on the frames and then just find the difference between 2 pixels or 2 frames and then just extracted the important area out of it and then reshaped it to 500 cross 500 cross 500. After that, I applied SVD sampler to that. To each and every frame, I wanted the information so that I can compare if every next frame has some information or not. So either I could have used a VLM, which would again be a very highly computationally expensive thing. So I tried with the SVD. SVD gave me 3 metrics, where the central matrix is the diagonal matrix. I took the diagonal elements and created one vector for every frame. So now if I am having n frames, I am having n vectors. I normalize that, I get probabilities, and then I applied KL divergence to that. Now after applying KL divergence, I get to know that how each frame is different from the other one. Now just we apply the threshold, and the threshold is also dynamically calculated for each and every video using the mean of KL divergence plus alpha into the standard deviation. After that, so it's a whole dynamic process, nothing is fixed in this process. The video will be given as input and we'll get the important frames. The next part was, we applied RTMW to it. RTMW will give me poses. It will give me some biomarkers, which like I had my fingers and elbows. So it gave me approximately 65 points. So now, instead of passing a 512 cross 512 number of pixels or number of data points, I am just passing 65 points. So it's like we have converted a very high dimensional space to a very low dimensional space, and which can be trained very easily. And also we applied some node dropout to it. Node dropout is like while passing the video to the model, entirely drop this hand. Why it is done? It is done to prevent overfitting, because otherwise what was happening, because deep learning is a very powerful tool, it was trying to memorize that who is the signer and what type of activity is going to happen, like by just knowing the distance between 2 hands and that. So that's why it was applied to tackle the overfitting. After that, we got this sort of structure here. Then we applied a part GCN. There was a research paper in CVPR. I took that as a reference. So what I did, I applied a separate GCN for left hand, a separate GCN for right hand, and a separate GCN for all these things together. Now there were 2 reasons to do this. The first one is because GCN is a of n square process. So as the number of nodes increases, the complexity increase. And the second thing, I applied it to the local area to get more finely refined activities. So that was the whole idea of this part GCN. After that, we applied a continuous dual positional encoding. We'll talk about this. And then we passed the data to the elastic transformer, and finally we did the classification. In the classification, we also apply arcface. What it does, like, it doesn't improve your test accuracy, but it creates some margins between the clusters, and it try to reduce the overfitting. So this is about the SVD. As I already told you about it, I applied SVD, metrics, and then I applied the K divergence on that. The efficiency gain from this was, there was no data set available, so we collected it by own. So it was like 120 watts, about 9.5k videos, and the average frames per video was 42.2. And after applying this K divergence and SVD, we reduced it to 13.2 frames per video. It was like approximately 70% reduce in number of frames. So this is exactly like, this is how the pre-processing looks like. This is the initial video. We get to know about the important area where the activity is being happening. Then we just get that area. We apply SVD and K divergence. We get these frames, and then we apply RTM post to this. Now these are the biomarkers. Now if you can see one thing, it is like frame 1, frame 3, frame 9, frame 11, frame 13. So the difference between each frame is varying. It's not like a uniform distribution like frame 1, 5th, 10th. But if I pass this, if I talk about the normal transformer architecture, it assumes that each and every data point which is passed in this has some uniform distribution or some uniform temporal difference, which is not in this case, which is the problem. In the GCN, what we did, first of all, we tried to pass all the 65 points as it is, just their coordinates. But what happened? The GCN was assuming that this point is connected to I also. My hand is also connected to I because we have given that information to it. So after that, what we did, we added 8 features to it: the XY coordinate, the velocity of XY coordinate, the spatial bone vector. Like, this finger will only be connected to my this elbow. It will not be connected to my face. If I just pass this directly to the model, the model will have to find it by its own that, okay, this is not a connection I have to make. So that's what we did here. Now about the continuous dual position encoding in elastic transformer. As I told you that the temporal information is now not preserved because it's not a uniform sequence. So what we did, we take two types of sequence. Let's say, if I go back to this one, let's say there are frame 1, 3, 9, 11, 13. So the one type of sequence will be the absolute sequence, same as it is 1, 3, 9, 11. And the second type of position encoding will do is like the relative position encoding. Like, if this is the selected frames, I will consider this as a video, and in this scenario what will happen, this is 1, 2, 3, 4. So like, there are two types of position encoding. One is absolute with respect to the actual video, and the second one with respect to the selected frames. And then we just concatenated that and added to the vector we got from GCN, which is like a standard process, and passed it to the transformer architecture. Now the dataset was about 120 classes, approximately 9.5 videos across 5 semantic categories. Like, by these categories I mean like some were related to medical field, some were related to education field, some were related to this application field. So these were all the categories. Average video per close basically means word was 78, and there was a strict protocol which we followed during the train test script to preserve data leakage. Is that, let's say a word is there and 120 people have done performed that word. So there is no same person doing the same activity in both the test and training set. So that thing has been preserved by us. So there is no data leakage in that scenario. The accuracy we get is 89.8% with a F1 score of 90.06, and that's also macro F1 score, which is highly recommended in the case of imbalanced dataset. And with a generalizability of just 3.5%, like it was 93 or 94% training accuracy. So that's pretty much a good generalization. And I'd say that we also tried with some baseline domain models like STGCN and CGI. We also tried with more architectures. I'm just displaying those the category which matches with the GCN. So the STGCN get 83% and this one get 64%. To test the robustness of our own architecture, we also tried a model on different publicly available dataset. This one is LC64, this is Argentina Sign Language dataset. We achieved a 99.18% accuracy on this. This is include 50 and include. This is also Indian Sign Language dataset. We also achieved 97.1 and 95.8% accuracy on this. So this basically shows that our model is pretty much robust in while working with different datasets. And now the dataset which we collected was just 15 frames per second. So there was a question if our architecture can work only with less number of frames. But these were like 60 FPS and 25 FPS, and it also worked there, so that also proved that FPS is not an issue. So the key features is it's very lightweight. It's just like 6.13 million parameters with a very high throughput. Like it was just having 2.87 milliseconds of latency when trained on RTX 4090. And we'd have to try to deploy in hardware. We haven't tried, but we think that we can deploy it on hardware using int80 quantization, but that's our future work. I can't promise it right now. Our future work also deals with, like this was a word level classification. We will also, our next step will be to collect the sentence level data and try to predict that as well. So that's all about my research work. Thank you, and I'm open to questions.
Thank you for your excellent presentation. Can you go back to one slide? And you talk about these non-manual markers. So do you have some ideas how to include them in the evaluation in the future? You have this point about the non-manual markers. So do you have some idea how they can be included to refine the evaluation in the future?
Actually, this thing is like our architecture is very much based on RTM pose. If the RTM pose is unable to find the markers, then the whole process will be collapsed. So that's what it's like. If the markers, we can't find the markers, we can't do the next process. So that's a very crucial step in that. So if that's broken, our entire pipeline is broken. So that's what we are trying to do. If we can do it something like that way, if RTM pose doesn't work, something else should be there as a fallback option. So that's the part of research we are trying to do.
And so the sign languages because I understand sign languages are different from country to country,
yes,
etc.
Yes.
But you evaluate, and India has so many languages. So do you have a standard sign language?
Yeah. So there are 22 official languages which are spoken languages,
yes,
and a lot of thousands of unofficial languages. Yes. But sign language is a pretty much standard. It's not. It doesn't vary state to state. It's for the whole country.
Oh, okay.
Yeah.
Okay. That's very nice. Thank you.
Yes.
Everyone seems happy?
Thank you for the excellent presentation. I just had a quick question about the GCN layers that you added. So as I understand it, you have a separate GCN for the left hand and the right hand, as opposed to doing one across the whole body pose. I was just curious if you tried doing both ways and then decided, or it was just like based on prior research?
Actually, there was a research paper on CVPR, as I told. There they tried this thing to do everything like separate for the left hand, separate for the right hand. That's what exactly I have done. It's like I've taken that part of their research. It's not entirely my new idea. Yeah.
Okay, but then generally it's better to kind of have the separation instead of having one GCN for the entire pose. So that's like, in my head that sounded a bit counterintuitive, so I was just trying to understand.
Yeah, that's why there are three GCNs working together.
Yeah.
The one GCN is for the left part, one GCN is for the right hand, and the third GCN is where it is. And the third GCN is for the entire body.
Okay.
Yeah, it's like one for this, and for the third one, we will not work like we will not worry about the very detailed one. We will consider one point, so that number of nodes doesn't skyrocket, and then we do it for the entire body pose.
Okay.
the end. Thanks very much.
Thank you.